We're about to pull back the curtain on a world that's almost completely hidden from view, a world of, well, invisible engineering that powers literally everything you do, from flipping a light switch to trusting the food in your fridge. We're going to dive into the super high-stakes field of industrial automation. I mean, have you ever really stopped to think about what it takes to keep our society, well, running? Who's the person making sure the power grid doesn't just collapse, or that the food you buy is actually safe, or that these massive factories can run 24/7 without some kind of catastrophic failure? Well, the answer is this whole army of what you could call invisible engineers. They're the ones behind the scenes, designing and troubleshooting these unbelievably complex systems that form the backbone of our entire civilization. And they're solving problems most of us don't even know exist. So, to make this invisible world a little more visible, we're going to follow the career of one senior systems engineer. Over the course of 2 decades, their projects are going to give us this amazing window into some of the toughest challenges out there in industrial automation. So, our engineer's first challenge? Oh, it's a massive one. Just, keeping an entire nation's power grid from collapsing. It's this constant, delicate balancing act that has to happen at pretty much the speed of light. Think about it for a second. When millions of people all turn on their air conditioners at once during a heat wave, or a giant cloud suddenly blocks a massive solar farm, what stops the whole system from just crashing? What actually keeps the lights on? The answer is a system called Frequency Control Ancillary Services, or FCAS for short. Honestly, the easiest way to think about it is like the grid's super-fast reflex system. Its one and only job is to keep our electricity perfectly stable at 50 hertz by instantly, and I mean instantly, reacting to any little imbalance between power supply and demand. And when I say fast, I mean fast. This table here breaks down the different response times the grid needs. You've got services that react in minutes or seconds, which is already pretty quick. But just look at that very fast category at the top. It needs a response in less than 1 second, and the system is being monitored every 50 to 100 milliseconds. That's insane. Just let that sink in. 1 second. That is the entire window these engineers have to stop a sudden drop in power from cascading into a massive, widespread blackout. It is an absolutely incredible feat of high-speed control engineering. All right, so from the massive scale of an entire country's power grid, our engineers' work now takes us inside a single industrial plant. Here, the challenge shifts. Now it's about building an efficiency engine, a system designed to prevent catastrophic failure while squeezing every last drop of productivity out of these giant machines. Okay, so this might just look like a complicated equation, but to an engineer, this formula is what stops a multi-million-dollar machine from literally tearing itself apart. It calculates something called the surge margin. In simple terms, it stops the airflow inside a giant compressor from violently reversing direction, which, would be catastrophic. Now, if that surge formula is all about preventing disaster, this next one is all about measuring success. It's called OEE, which stands for Overall Equipment Effectiveness. You can basically think of it as the ultimate report card for any factory. It is the gold standard for measuring just how productive a manufacturing line really is. OEE breaks down a machine's performance into 3 really simple but powerful questions. First, availability. How much time is the machine actually running? Second, performance. How fast is it going compared to its absolute top speed? And third, quality. Of the things it's making, how many are actually good parts? You multiply those 3 together, and you get a single score. A world-class factory, by the way, is aiming for 85% or higher, and even a 1% improvement can mean millions of dollars. Okay, now we're moving into environments where the stakes are even higher. We're talking about places where a single spark could be completely devastating. This is engineering for safety under extreme pressure. So designing a control system for something like a pump in an oil refinery, man, it's an exercise in extreme caution. Engineers have to classify every single zone based on its explosion risk. Then they have to pick specially certified equipment that's guaranteed not to create a spark. And on top of all that, they build in layers of redundancy, so if one part fails, a backup instantly takes over. The whole goal is to make sure no single point of failure can cause a disaster. And this whole safety-first philosophy, it extends to massive machinery too. When you're automating something like a giant industrial crane, you use these special controllers called fail-safe CPUs.
If these systems detect any kind of problem, a broken sensor, a weird signal, they are programmed to do one thing and one thing only: automatically bring that massive machine to a safe stop. It's all about protecting the people working around it.
And all this focus on data and safety, it leads us right into the modern era of manufacturing. We're talking about the blueprint for the smart factory, connecting everything from the tiniest sensor on the factory floor all the way up to the cloud.
This table basically shows you the journey of a single piece of data in one of these smart factories. It starts at a sensor, goes to a local gateway, and then up to a cloud database. But the really clever part, the bit I love, is highlighted right there in the admin UI row. This is where the engineers got really creative. So to let the plant managers change really complex settings, like production schedules or product formulas, without needing to be a computer programmer, the engineers built a user interface using Google Sheets. It's just a brilliant example of using a simple, familiar tool that everybody knows how to use to control a super complex industrial system. You know, all of this brings us to a really crucial point that's been hiding underneath all these projects. It's not just about the wires and the code. It's about a philosophy of systems thinking. It's the art of translating a big idea into a functioning reality. Really great engineering relies on this discipline called requirements traceability. It's just a structured way of thinking that makes sure you never lose sight of the original goal. You start at the top, the business layer. What are we actually trying to do here? Then you move to the project layer. What are the physical and legal rules we have to follow? And only then, at the very end, do you get to the hardware layer and ask, what specific tools do we need to buy? It stops you from getting distracted by cool tech that doesn't actually solve the client's problem. And that right there, that really gets to the heart of what a systems engineer does. They're translators. They take the client's what they want, the user requirement specification, and they turn it into a detailed technical blueprint for the how, the functional design specification. Getting that translation absolutely perfect is the whole game. So, as we wrap up this little journey through the hidden world of industrial automation, it kind of leaves us with one final question. The next time you flip a light switch, or open your fridge, or just see a factory off in the distance, take a second and ask yourself, what invisible engineering is powering my world right now?